Hello, welcome to the first online lecture for heat and mass transfer in the Chemical Engineering Department of UJ. My name is Anna Microsoft. I'll be reading the notes of the slides for you. These will also be available to you in the PowerPoint file on Blackboard. After the lecture, a survey on Blackboard will be available for you to give feedback on the experience. Anyway, let's get back to business. Today you are going to deal with heat transfer during boiling and condensation. Here you have an example of boiling in a beaker filled with water. Heat is provided at the bottom. Due to the heating, the water reaches boiling temperature after some time. Water vapor bubbles form. Okay, the water is boiling now. Can you tell me what the temperature of the water is? Do you know? Are you sure? Did you say 100 degrees centigrade? Yes, that would be correct if the pressure of the surroundings were 1 atmosphere. As the vapor or steam bubbles move up due to buoyancy, water streams in from the side to replace the volume. Hence you have convection heat transfer. As you saw before, this is heat transfer from a surface to a moving fluid. As you know, boiling can be quite vigorous, hence you can expect a high heat transfer coefficient. After time goes by, the level of boiling water drops. This is due to water escaping as steam. Does the temperature increase or remain at 100 degrees centigrade? What do you think? You are right, it remains at 100 degrees centigrade. If this is so, then where does the heat added go if the temperature remains constant? Let me give you a hint, it is converted to some other form of heat. It is converted to the form of heat that results in water evaporating. Alright, if you said latent heat, you are correct. Latent heat is an important physical property. It is equal to the latent heat required to boil water divided by the mass of water that is boiled. Hence it is also equal to the rate of heat addition divided by the rate of evaporation. The rate of evaporation, m dot, is therefore equal to the rate of heat addition, q, divided by the latent heat, hf fluid g gas. Latent heat can be looked up on table A6. For boiling at 100 degrees centigrade, which is equal to 373.15 Kelvin, the latent heat is 2257 kilojoules per kilogram. So now, what should you know about boiling? As you saw in the previous slide, latent heat is an important physical property. As temperature is mostly constant, and heat is used as latent heat to boil the liquid, you have a large heat flow rate for a small temperature difference. Surface tension plays a role in the formation of vapor bubbles. Buoyancy forces cause vapor bubbles to rise and this results in convection. As you probably know, the formation of bubbles can be quite intense and vigorous, and this leads to a large heat transfer coefficient. This is because you would expect a large advection component in the convection. You may know that boiling of a liquid is used in refrigeration at low pressure and low temperature. As with other forms of convection, the Nusselt number in boiling convection has been found to be a function of various dimensionless numbers. These dimensionless numbers include the Jacob number, the Prandtl number, and the Bond number. The surface involved in transferring heat to liquid during boiling has a temperature of Ts. The temperature of the boiling liquid can be taken to be the saturation temperature at the given pressure, or Tsat. For heat to be transferred from the surface to the boiling liquid, Ts has to be greater than Tsat. Newton's law of cooling can also be applied to boiling. Ts minus Tsat is known as the excess temperature, or delta Te. In this BTEC course, you are going to consider pool boiling and forced convection boiling. If you are given a set of conditions in a test, for example, you will have to identify which type of boiling applies. Nukiyama spent a lot of time during his BTEC project on boiling water by passing electricity through a wire. He increased and decreased power by increasing and decreasing the flow of current through his wire. This is as power is equal to the voltage difference, E, times the current I. He calculated Q double dash by dividing power by surface area of the wire. He measured the surface temperature of his wire, and could therefore calculate delta Te, the excess temperature. He used the data collected to construct the boiling curve at 1 atmosphere pressure. In the previous slide, you saw how Nukiyama varied Q double dash and then measured delta Te. This graph is the result of that, with Q double dash plotted on the y-axis and delta Te plotted on the x-axis. Note that Q double dash is the heat flux and delta Te is the excess temperature. When Nukiyama increased the heat flux from 0, the excess temperature increased and reached 5 degrees centigrade, at which point the water started boiling visibly with the formation of vapor. This is the onset of boiling point on the graph, or ONB. From 1 degree up to the onset of boiling, the boiling regime is classical free convection, with heat being transferred from a wire surface to the water that is moving due to buoyancy. Due to increased convection after the onset of boiling, the heat flux had to be increased even more rapidly to get a given excess temperature increase. However, the excess temperature increased more rapidly when the critical heat flux was approached. The critical heat flux is Q double dash max on the graph. From the onset of boiling to the critical heat flux, the boiling regime is nucleate boiling. This is as you often have imperfect sites on the hot surface that heat up more and act as nuclei for the production of vapor bubbles. Here convection heat transfer is increased due to advection caused by rising bubbles of steam. As you approach the critical heat flux, however, more and more of the hot surface becomes covered in vapor. Heat transfer from a surface to a vapor is slower due to the low conductivity of the vapor. This then more and more cancels the positive advection effect of rising vapor, causing the maximum heat flux to be reached. What do you think happened to the excess temperature when Nukiyama increased the heat flux to above Q double dash max? Did it stay at 30 degrees centigrade? Did it decrease rapidly? Or did it increase rapidly? Actually, what happened was that the surface temperature and hence the excess temperature increased so rapidly that poor Nukiyama's wire melted every time he tried the experiment again. Had Nukiyama controlled the excess temperature instead of the heat flux would have decreased from critical as shown in the graph, down to a minimum at the latent frost point. If only Nukiyama had known the true form of the boiling curve, now he bought many wires thereby using up the BTEC equipment budget for the whole year. From the critical heat flux to the latent frost point, the vapor film covering the surface expands until the whole surface of the wire is covered by vapor and all water is driven off. This change resulted in the boiling regime being called the transition boiling regime. The heat flux decreases due to the lower heat transfer coefficient of the vapor compared to a high heat transfer coefficient for vigorously boiling water. The reason for the low vapor heat transfer coefficient is the low thermal conductivity of the vapor. At the latent frost point, the whole surface is covered by a vapor film. From this point onwards, the heat flux increases with increasing excess temperature as predicted by Newton's law of cooling. This law states that Q double dash equals the heat transfer coefficient times the excess temperature. Increasing the excess temperature would therefore increase the heat flux. From the latent frost point onwards, the heated surface is totally covered by a film of vapor, and you have the filmed boiling region. It is very important to know the boiling curve so that you can identify the boiling regime of a problem, and use the corresponding boiling correlation in a test, or an exam, or in industry. This is the correlation you need to use in the nucleate boiling region. Do you remember the range of excess temperature, delta T, for which we have nucleate boiling? Okay, here is the boiling curve again. Can you identify where we have nucleate boiling? Or can you not? Let me remind you. It is from the onset of boiling to the critical heat flux maximum. In other words, from an excess temperature of 5 degrees, to an excess temperature of 30 degrees. Look at the following example. Say we have water boiling at 1 atmosphere over a surface that has a temperature of 120 degrees centigrade. Do you think we have nucleate boiling in this case? Answer yes, or no. To give you a hint, you first need to calculate the excess temperature. This is equal to the temperature of the surface minus the boiling temperature. So, if you have a surface temperature of 120 degrees centigrade, the excess temperature is 120 minus 100 degrees centigrade, or 20 degrees centigrade. This is between 5 and 30 degrees, so you will have nucleate boiling. In this case, you can use the nucleate boiling correlation shown on this slide here. In the equation, sigma is the surface tension of the boiling fluid, and not the Stephen-Boltzmann constant. Also, in the equation, CSF and N are obtained from table 10.1 for the appropriate surface fluid combination. Q double dash can be calculated directly without using Newton's law of cooling. This is the correlation you need to use to estimate the critical heat flux. Do you know where the critical heat flux is on the boiling curve? In case you are unsure, here is the boiling curve again. The critical heat flux is at 30 degrees centigrade excess temperature. Note that this corresponds to a surface temperature of 130 degrees centigrade. Also note that, as the boiling curve is for water, these values are for water only. For another fluid, you would have to use a different boiling curve. The subscripts, V and L, refer to vapor and liquid properties respectively. The maximum Q double dash can be calculated directly without the help of Newton's law of cooling. The characteristic length must be much greater than the bubble diameter. For example, say you have a spherical surface. Its diameter must then be much greater than the diameter of the vapor bubbles that form due to boiling. This is the correlation you need to use to estimate the minimum heat flux. Do you know where the minimum heat flux is on the boiling curve? In case you are unsure, here is the boiling curve again. The minimum heat flux is at 120 degrees centigrade excess temperature. Note that this corresponds to a surface temperature of 220 degrees centigrade. Also note that, as the boiling curve is for water, these values are for water only. The minimum Q double dash can be calculated directly without the help of Newton's law of cooling. The correlation only holds for a large flat plate, and only for low pressures as C has a value of 0.09. For the nucleate boiling, critical heat flux and minimum heat flux correlations, saturated temperatures are used to calculate physical properties. Check the examples in the textbook to confirm this. This is a convection correlation you need to calculate the Nusselt number for film boiling. Do you remember the range of excess temperature, delta T, for which we have film boiling? In case you are unsure, here is the boiling curve again. Film boiling for water occurs for excess temperatures higher than 120 degrees centigrade excess temperature. The Nusselt number, and then the heat transfer coefficient can be calculated using this correlation. The heat flux can then be determined using Newton's law of cooling. The correlation applies for low surface temperatures less than 300 degrees centigrade. Note that the main mode of heat transfer is convection through the vapor film. The vapor film is at a temperature of Tf, the film temperature. The film temperature is equal to the temperature of the boiling liquid, Tsat, plus the temperature of the surface, Ts, divided by 2. You need to obtain the vapor properties at the film temperature. The boiling liquid is at the saturated temperature, hence you need to obtain the density of the liquid at the saturation temperature, or Tsat. If the surface temperature is higher than 300 degrees centigrade, then radiation from the surface through the vapor film to the boiling liquid becomes significant and has to be taken into account. You will need to calculate the average radiation heat transfer coefficient, h-bar-rad. Note that, if the formula for heat transfer coefficient due to radiation is plugged into Newton's law of cooling, it becomes the Stephen-Boltzmann law. You will also need to calculate the convection heat transfer coefficient, h-bar-conv, as you saw in the previous slide. After calculating the heat transfer coefficient for convection and radiation, you could use the first equation to calculate the effective heat transfer coefficient. However, if the heat transfer coefficient due to radiation is less than that for convection, you will use the second equation to calculate the effective heat transfer coefficient. If boiling liquid flows over a cylinder, you have forced convection boiling. For low velocity of water, you can use the following correlation. We is the Weber number, and depends on the surface tension, given by sigma. For high velocity of water, you can use the following correlation. Check this, but I think that you need to determine the physical properties for the correlations in this slide, using saturated temperature. Use the following expression to check whether the velocity of water is high or low. I suggest you then calculate Q double dash max divided by rho v, hfg, v, for low and high velocity. The values obtained can be checked against the third equation to see if the velocity is high or low. Once you have done all of this, you can solve for the appropriate Q double dash max.
Hello, my name is David Microsoft, and I will be taking over from Anna for this part of the lecture. There are two types of condensation, dropwise, and film condensation, and you will be concentrating on the film type. On the left-hand side of the slide you have a surface which is in contact with a heat sink. This has caused vapor to condense on the surface in the form of a liquid film. The liquid molecules have little energy, so they vibrate slowly, as will be illustrated by the simulation once it is triggered. Vapor molecules have more energy. Once a vapor molecule comes into contact with the liquid film, it can lose its latent heat. If it does this, it will condense, as it no longer has enough energy to whiz around in the vapor. As you see, the latent heat, liberated from the vapor molecule, then moves through the liquid film to the surface, which is at a temperature lower than the saturation temperature. This happens due to the conduction heat transfer mode. When the heat reaches the surface, it is removed by the heat sink. The diagram shows the boundary layer for film condensation on a vertical surface. You have liquid against the vertical surface, and vapor adjacent to it. As you move down the surface, the thickness of liquid increases. This is because vapor condenses everywhere. The resulting condensate then moves down and meets up with additional condensing vapor, thereby increasing the thickness of the liquid layer. At the surface of the liquid film on the vapor side, the temperature is Tsat, because this is where condensation takes place. The temperature then decreases as the cooling surface is approached. At this surface, the temperature is maintained at Ts by the heat sink. The velocity profile is also given, with both vapor and liquid moving at the liquid-vapor interface, and the velocity of liquid at the vertical surface being 0. The Nusselt analysis and simplification of the condensation boundary layer is given here. The temperature of the vapor is assumed to be at saturation. This means that the thermal resistance through the vapor film next to the liquid is neglected. The velocity of the fluid approaching the liquid-vapor interface is assumed not to change. Consider the differential height increment dx. A flow rate of m dot enters at the top. This is joined by a small flow rate dm dot, that condenses from the vapor. The total mass flows out the bottom. Note that dm dot is equal to the small amount of latent heat, dq, that is emitted from the condensing vapor, divided by hfg. The heat flow to the surface is q double dash times b times dx. What does b times dx represent? Well, if you have not got it yet, b represents the width of the plate. If this is so, what does b times dx represent? If you answered the area of heat transfer, you are correct. Remember, for conduction, the area of heat transfer is perpendicular to the heat transfer direction. The total heat transfer rate to the surface can be calculated using Newton's law of cooling, and the average heat transfer coefficient from the top to the bottom of the vertical surface. Note that the saturation temperature is higher than the surface temperature. The total condensation rate can be calculated using the total heat transfer rate, divided by a modified latent heat, HFG-. Condensation has its own Reynolds number, which depends on the total condensation rate, m dot. Here b is the breadth of the vertical surface. Note that the Reynolds number must be less than 30 for the flow to be laminar. Nusselt derived a laminar film condensation correlation. This is for Reynolds numbers that are less than 30. A modified form of the latent heat of formation term was developed by Rosenau, to account for subcooling of the condensate to an average temperature of Tf. As can be seen from the diagram, the liquid is at a temperature between Ts and Tsat. Hence the film temperature is used to determine the liquid properties. The vapor is at a temperature of Tsat, and the condensation also happens at the liquid-vapor interface at Tsat. Hence you should obtain ρV, and HFG, at Tsat. Three flow regions have been identified for condensation. The first is laminar, wave-free flow, for Reynolds numbers less than 30. The second region is laminar, wavy flow, for Reynolds numbers between 30 and 1800. If the Reynolds number is greater than 1800, you have turbulent flow. Correlations for each of these regions are given in the next slide. Firstly, for a Reynolds number less than 30, the correlation is as follows. V is the kinematic viscosity, equal to viscosity divided by density. For wavy laminar flow, the correlation is as follows. Finally, for turbulent flow, the correlation is as follows. Note that h bar L, and Reynolds number, can be written in terms of m dot, using Newton's law of cooling, and the definition of Reynolds number. Hence you can potentially solve for m dot, the condensation rate. This is the end of the lecture. I hope that you found the experience interesting. Please do the survey on Blackboard to share your thoughts. Thank you.